Hello, and welcome to this edition of Scientists in Action. Before we begin, I would first like to say that the Denver Museum of Nature and Science respectfully acknowledges that the land we are on today is the traditional and ancestral homelands of the Cheyenne, Arapaho, and Ute nations and people. We also recognize that the lands that are now called Colorado also represent the traditional and ancestral homelands of dozens of different Native American tribes and nations, people who now reside in the American Southwest, the Great Plains, and the Rocky Mountain region. Thank you. And let's begin with this edition of Scientists in Action, a virtual voyage through the universe. So before we begin, I'd like to take care of just a couple different housekeeping items. Firstly, if you are one of our on-camera schools today, please keep your camera off and your microphone muted. We'll prompt you when it is time for our question and answer segment. And if you are not joining us on camera, nonetheless, thank you for being with us today. We love to hear your questions, so please enter those into the chat, and we will answer as many of those as we can. My name is Asa Erlinson. I'm your host, but I'm not going to take up any more of your time, and instead I'm going to introduce our featured scientist of today, the Denver Museum's own Dr. Chun Yu. So hello, Chun. Thank you for joining us. And could you tell us a little bit about what you do and what are we going to be doing today?
Yeah, well, thank you very much, Asa. So as Asa says, I'm a scientist here at the Denver Museum of Nature and Science. I am an astronomer, and astronomers study the universe, basically anything outside of our planet Earth, and actually more like outside of our solar system. But the astronomers use tools like telescopes, and they can study other planets, they can study our sun, they can study other solar systems, other stars, even our entire galaxy and other galaxies. And there are some astronomers who study the entire universe. They're called cosmologists. Now, like I mentioned, astronomers often use telescopes. And even before telescopes, they use their eyes. And I think there was also an exercise that was sent out to teachers to have students look up in the nighttime sky. And I don't know how many kids did it, but if you did so and observed and drew what you observed, I encourage you to email it in to us. But you were asked to observe the Big Dipper. And here is just a picture of what the constellation looks like. It's towards the northern part of the sky. And it actually does change its orientation over the course of the night as the Earth turns. And so I think we have some pictures of images that students had sent in. And so here is one with what looks like a lamppost and a tree in the center, and a picture of images of how the Big Dipper appear to have changed over the course of the night. And then I think we have another one which shows possibly a hill or a horizon. And the student even wrote down the time and the date or the day of the week. And so these are wonderful observations and wonderful note-taking. And these are examples of what scientists would actually do. And if you go out and do this, observe and record, you're doing exactly what a scientist would. You have to go out and make an observation and write down and record your observation in such a way that you can share it with other people. Now, astronomers obviously do it in a much more complicated way. We use telescopes nowadays, and these telescopes can both be on the ground, on the surface of the ground, as well as up in space. But astronomers use them to record images and spectra and information from planets and stars. And we also have our robotic explorers out there too, in spacecraft and on rovers, getting information. And all this information can be fed into a simulation. So what you're looking at behind me is not just a picture, but it's actually a simulation of the known universe, and I can actually fly around. We're starting off at the Earth, but we can go anywhere that we want. And all this information that astronomers, thousands of astronomers have accumulated, can be fed into creating the simulation. And this virtual tour of the universe will allow us to travel to distant parts of our solar system and our universe. And more importantly, we will be asking you, the students and the classrooms, to tell us where you want to go. And so that's what makes this super special. And so this brings us to our first poll. And what we're going to do is we're going to ask you to figure out where we want to go in the inner solar system. So which rocky planet do you want to visit? Do you want to visit Mercury, or Venus, Earth, or Mars? So for teachers who are handling an entire classroom, you can poll your entire class and enter one of those 4 choices into the Zoom poll. And we'll take just a few more seconds to wait for all the entries to come in. So these are rocky or terrestrial or Earth-like planets. And that's because most of the planet is either rock or some metal at the center of the planet. And if there is an atmosphere, the atmosphere is pretty thin compared to the rest of the body of the planet. So I think we're coming up to the end of the poll. And so let's see which one we will be visiting. All right, so it looks like we're going to be going to Mars. Mars wins by 63% of the vote. So we're at Earth, and what we're going to do is we're going to go ahead and fly ourselves to Mars. And we have to fly through part of the solar system to do so. And as we come up on Mars, you can see 2 orbits of Mars's 2 moons. And after staring at the Earth behind me, you'll notice that Mars looks very, very different from the Earth. It doesn't have the oceans. It doesn't have any obvious bodies of water. There's no blue of the oceans. There aren't any obvious clouds on Mars, although Mars does have some clouds. But as we come down and zoom down onto the surface, you see a very dry, dusty surface that's peppered by craters. So all these round looking things are explosions caused by impacting asteroids and comets and meteors that hit the surface with enough energy that they explode and they carve out these round shapes. But when we look at Mars, we'll also see lots of features that look like they might have been caused by running water. So even though we don't see any water on the surface today, we don't see any big bodies of water, we can definitely still see things that look like river channels off to the left of center here. There looks like a river channel that splits up into 2, running vertically, and then off to the kind of the center, and we can see a bunch of landscapes that look like they've been carved by running water, so the water has eroded away. So this presents kind of a mystery because the fact that there isn't any water now suggests that Mars must have had water in the past, perhaps billions of years ago, and it's subsequently lost that water. We think some of it remains frozen underneath the surface, but the rest of it escaped into space. So Mars is a very peculiar type of place. All right, so now that we've looked at Mars, I think we have another poll, which is to look at the next set of planets. So not just the inner planets, but we want to take a look at the outer planets as well. And these are the gas planets, the gas giants. And again, we have 4 choices to look at: Jupiter, Saturn, Uranus or Uranus, and Neptune. So which one of these do you want to visit next? And unlike the inner rocky planets, the gas giants are much larger, as their name suggests. And instead of seeing a surface like we can see the surfaces of Earth and Mars. We can't see the surfaces of any of these planets because they're hidden behind thick, thick atmospheres that are thousands of miles deep. So you'd have to travel a long time before you hit surface. So I think we're going to have a few more seconds before the poll closes. So which of the gas giants do you want to visit? Are you coming up onto the end of the poll? And we are going to Jupiter with 50% of the vote. All right, that not definitely hit 50%. So with Saturn being the next most popular, but we will be flying to Jupiter instead. So here we're going to again fly past a bunch of the moons and their orbits around Jupiter. And Jupiter is the largest planet in our solar system. If you were to put the Earth right next to Jupiter, Jupiter would be 11 times wider than our own planet Earth. And unlike Mars or Earth, as you can see, we don't really see any surface to Jupiter. We're seeing the cloud tops. And you see lots of swirling patterns on the clouds of Jupiter. And if you've ever watched the TV news and they do the weather report and they show satellite imagery of the Earth, you can often see clouds and cloud patterns and clouds making up storms here on the Earth. And the exact same thing is happening on Jupiter, except that you don't see through the clouds because the clouds dominate the entire atmosphere. The clouds come in different colors. They're oranges and reds and browns and yellows and whites. And there's also this gigantic great red spot, which is an enormous storm that's been running in Jupiter for hundreds of years. It's a storm that's 10,000 miles across. So it's absolutely enormous. And it's been ongoing since we've started observing Jupiter with enough detail to see it through telescopes. So here is Jupiter. And I think what we can do next, Asa, is we are ready for the first round of questions from the students.
Absolutely, yeah. So we'll now turn our attention to our on-camera schools. We'll first introduce Bridges Elementary. So Bridges Elementary, if you will turn your camera on and turn on your microphone. And we are looking forward to seeing and hearing about, what are you wondering? What questions do you have about space today?
Has an asteroid ever hit the International Space Station?
Has an asteroid ever hit the International Space Station? Okay. Well, if it did, the International Space Station probably wouldn't be there anymore. So let me let's see if we can get to the International Space Station. So the International Space Station is orbiting around the Earth. So we have to go back all the way back to planet Earth. And there's actually a label for it. So let's zoom in. And as you can see, the ISS is orbiting actually really close to the Earth. There we are. And it only orbits a little bit over. Hold on. I have to do something real quick here. I'm sorry, lost a window. As I said, the International Space Station orbits just over 200 miles above the surface of the Earth. So that's super, super close. I mean, if you've been on road trips, you've probably traveled 200 miles over the course of a day on a road trip. And so if your family car was able to magically drive straight up into the air, you'd arrive at where the International Space Station is in orbit around the Earth in just a few hours. But it's our largest space station that we've ever built and put up into Earth orbit. It's about the size of a football field from end to end. So from one end of the solar panels on the left all the way to the other end. But as you can see, it's not completely filled in. It consists of a bunch of modules that are much smaller than a football field. And each of these have been put up over time using individual rockets, as well as the space shuttle, which no longer flies. And There has been worry about small meteorites or meteors hitting and puncturing holes in the space station. And so far, I mean, there have been some air leaks that have been plugged, and it's not entirely clear whether they're due to something from space hitting it. But you can imagine if something really big was to hit it, it would cause a lot of damage. And that's just because when things are in space, they can travel really, really fast. So the International Space Station is moving about at least 12,000 to 15,000 miles per hour around the Earth. And things in space and orbit around the sun can travel many tens of thousands of miles per hour. So if something big was to hit the space station, you can imagine it causing a huge amount of damage. So thankfully, it hasn't been hit by anything large like an asteroid, but it might have been hit by smaller micrometeoroids, so something maybe as small as a speck of sand. That's a great question. Do you have another one from that same school?
Yeah, let's head back to Bridges. What else are you wondering?
I'm wondering how hot Mars's core is.
How hot Mars's core is? That is a question that I can't actually answer. I do know that Mars, like the other terrestrial planets, does have a core. The inside or the center of the world is warmer than the outside. And so Mars is about 50% further away from the sun than the Earth is. And so it receives less light and less heat from the sun. And it also has a thin atmosphere, making it harder to keep heat on the surface of the planet. And so even though on the equator, on the surface of Mars, on a warm summer day, you might get temperatures as high as 70 degrees. For the most part, Mars is actually a very, very cold world. So it's not uncommon for Mars to have lows of minus 200 degrees Fahrenheit. And so the surface of Mars is definitely colder than the Earth in general. And there is some residual heat on Mars, but because Mars is a much smaller world than the Earth, it's also lost a lot of that heat. But there is still some heat, but I don't actually know off the top of my head what the temperature of the very center of Mars is. One way to think about why planets stay warm. So the Earth has a liquid molten outer core, whereas Mars might have a small amount of molten rock in the core, but for the most part, there's far less heat. And that's because Mars is a lot smaller, and so the heat radiates away. Just like if you took a boiling egg, a hard-boiled egg out of boiling water, that tends to cool off a lot faster than if you took like a big pot roast out of the oven, which takes much longer to cool off because it's a lot bigger. Okay, are we staying with the same school, Asa, or are we going to the next school?
Yeah, let's get two more questions from Bridges Elementary. So this one will be our third.
Okay.
Okay, I was wondering, why does like Mars and Jupiter not have like water, but Earth does?
Okay, that's an excellent question. So why do these planets seem not to have any water? And so I'll take up Mars first. Like I said, Mars probably had water just because we see evidence of it. And here we can just fly down to a random part of the surface. And you can see features that look like they might have been carved by running water. Have you ever played with mud pies or had a hose in your backyard and played with mud? You can see a lot of the same sort of features as you have running water carve out the dirt. And we think part of the reason is that Mars, because it's smaller, it actually lost a lot of its atmosphere over time. And so it's small enough that the gravity of the planet wasn't able to hold on to the atmosphere, and light from the sun would and particles from the solar wind would bounce off the atmosphere and cause atoms and molecules to get ejected out into space. And so for any water vapor in the atmosphere, it was thought that UV light would break up the water vapor into hydrogen and oxygen, and those lighter molecules would then escape, the hydrogen atoms would escape into space. And so over time, Mars lost water. Now, as far as Jupiter goes, there probably is quite a bit of water in Jupiter, but it's in gaseous form. And because Jupiter does have enough gravity to hold on to whatever water it might have been formed with. And so a lot of that water would be in its atmosphere. And because we don't see the surface of Jupiter, there probably is a surface, but again, you have to dive through tens of thousands of miles of gas, of atmosphere to get to that surface. There's really no way to see that water. So whatever water might exist on Jupiter, it's probably in the form of water vapor in the atmosphere. That's a great question. And I think we have one last question.
That's right. One last question from Bridges Elementary. What are you wondering, friend?
Why do they always send rovers to Mars and not humans?
I mean, why do we send robots to Mars and not humans?
Rovers.
Rovers. Okay, yeah. Yeah, so we send rovers, which are also robots. And so Mars is the only planet that's completely been explored only by robotic machines. So both robots in orbit around Mars in the form of satellites, but also robots on the surface called rovers. And I think we also have a picture of what the surface of Mars looks like from one of these rovers. And part of the reason why we've sent robots or these rovers so far is that it's far easier and less expensive to send robots. If you send humans to Mars, not only do you have to send the scientific equipment and instruments that you'll be making your scientific measurements with, but you also have to send all the air, the water, and the food that humans need in order to survive. And that's because Mars really doesn't have any of that. And whereas a robot or a rover only needs an energy source like a battery or a set of solar panels in order to keep going. Now, of course, rovers aren't as capable as humans. And so there are a lot of people who want to eventually send humans to explore Mars, but that probably won't occur for another decade or 2 decades. So for now, we have robots exploring the surface.
Awesome. All right. Well, thank you to our friends at Bridges Elementary for those excellent questions. We'll now turn our attention over to Garden County School. So go ahead and turn your camera on and your microphone, and we'd love to hear what it is you're wondering.
I'm wondering, how was the sun made?
How was the sun made? All right, that's a wonderful question. So let's I'm going to go ahead and target the sun. And we can mute the scroll. Okay. So we've flown out to look at the solar system. And so you can see that we have the sun, and it's being orbited by the 4 inner planets, Mercury, Venus, Earth, and Mars. And then we have the orbits of 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. And if we tilt down, we can, we also have a bunch of icy comets that are in orbit outside of Neptune's orbit. And I think we can also toggle on the asteroids as well. But you can see that all of these objects orbit more or less in the same plane, meaning if you were to build a scale model of the solar system, you could basically fit everything inside a pizza box, or if you made a pizza box big enough. And this, the locations of all these give you clues as to how the solar system was formed. So it turned out that our solar system probably originated in a giant cloud of gas that collapsed due to gravity. And so as the gas fell inwards, most of it got pulled towards the center. That's because that's where most of the mass was headed towards. And that's where it all started out. And that ended up building the sun, and a very, very small fraction of the gas piled up into a disk, sort of like a big pizza on the outside in orbit around the sun. And the gas piled up inside the sun enough for the sun to ignite with nuclear fusion. So it provides nuclear energy to light and heat the planets. And the gas and dust in that disk outside of the sun later accreted or collapsed to form the planets and the asteroids and comets and everything else in the solar system. So basically, everything in the solar system formed out of the same body of gas. That's a great question.
Yeah, all right. What is another question? These have all been great, so we're ready to hear another.
How was the solar system made?
How is the solar system? I missed that again. How is the solar system?
Made.
How is it made?
Yeah.
Yeah, so that's the same answer that or a very similar question to what was asked before about how the sun originated, and the rest of the solar system originated with the sun. So I said earlier that the collapsing gas gave us the sun, and part of that gas also gave us the planets and all of the stuff, the smaller stuff that's in orbit around the sun, and we can toggle on the asteroids again. And then one of the other really remarkable things is I'm going to turn on time so that you can see the everything orbiting. But let's see if we can keep going here. So if you look at these orbits, you can tell that the objects orbiting close up in the solar system orbit faster than the objects orbiting further away. And so Mercury whips around super fast, and Venus slower, and then the Earth slower still. But there are also hundreds of thousands of asteroids that are also in orbit. And it turns out that the orbits of all these objects aren't always exactly circular, or they don't, and some of them wander, meaning they have orbits that take them closer in than others. And it's kind of hard to see, but you can sort of see that there are objects that are orbiting outside of the asteroid belt. And some of them have orbits closer to the Earth or to Venus or to Mercury. And so it turns out that there are objects in our solar system that can wander away from their original locations and closer to the planets. And so over time, the solar system, the orbits of objects, especially the smaller objects, can actually change. And we think that's what has happened, so that the asteroids and comets haven't necessarily been where they've been orbiting the whole time. And even the planets have changed in their orbits, some dramatically and more so than others. But the solar system is a very, very dynamic place. You know, first of all, with all this gas collapsing inwards to form the sun and to form the planets. And then later on, as all these objects are orbiting, they're very dynamic. They can actually change because of gravity causing the orbits of the objects to change. So that's a great question. So Asa, which questions are we going to next, or what school?
We can get 2 more questions from Garden County, and then we'll move on to some of the questions we have in the chat, which again, as we're going on, participants are welcome to throw your questions in the chat at any point, and then we'll get to those after we address our on-camera schools.
Why are black holes, stars, and planets spheres?
Okay, why are the objects that we've been looking at spherical or ball-shaped spheres? So let's, we can jump to a planet that almost no one ever picks when they have the poll, which is the planet Venus. And that's just because Venus doesn't really have very many features to look at because it's enshrouded in clouds. But as you can see, Venus is spherical like all the other objects. And the reason why Venus and the other planets and stars or balls or spheres is because of gravity. So everything in the universe that is made up of matter has some gravity in it. Even you and I and everyone in your classroom has a small amount of gravity just because we all have mass. Now, we don't have very much mass individually, so we don't feel each other's gravity. But if we are standing on a sufficiently large rock like the Earth, we can feel the gravity of the Earth pulling us down. And the gravity is basically due to all the matter in the rock pulling on you. And you can imagine the same thing happening with Venus or any other planet. And if all the material is pulling on itself, it will naturally gain a round or spherical shape. And that's just a matter of how gravity works. It just wants to pull everything inwards. And so things just naturally turn around. Now, it is possible to have things that are not spherical. So I'm going to jump to an object that is distinctly non-spherical. And this might look like an asteroid, and it might be a captured asteroid, but in fact, it is a moon of Mars. And I'm going to turn off, it looks like we have some weird effects. I'm going to turn off the asteroids. So this is Phobos, or no, actually, I think this is Deimos, which is, to make sure. Okay, that's Deimos, and this is Phobos. So this is a moon of Mars, and this is no bigger than a typical large city. So it might be about 10, 15 miles across. And as you can see, it's very potato-y shaped. It doesn't look round at all. And that's because Phobos is too small for the gravitational forces to pull it into a round shape. Whereas the planet that it orbits, Mars, is round. So even though Mars is half the size of the Earth, it's still large enough, it has enough matter or mass to make it round. Yeah, I think we have one more question from that school.
That's right. Yeah, one more question. Awesome question about the shapes of the other objects out there. But what are you wondering, friend?
What really is a black hole? And is it bright in a black hole because it sucks light in? And if anybody were to get sucked in a black hole, would they ever get out?
Okay, those are all great questions about black holes. And I think we have a picture of a black hole that we can show. So black hole comes about at the end stages of stars. Stars have to be much, much more massive, at least 8 times more massive than our sun to turn into a black hole. So don't worry, our sun will never become a black hole. But when a massive star dies, it explodes and the remainder of it can collapse inwards. And if that remainder, that remnant is big enough, it can turn into a black hole. And a black hole is an object that's so massive that no matter how fast you travel, if you get too close to a black hole, if you go past an imaginary boundary called an event horizon around the black hole, then you won't be able to escape, even if you're traveling as fast as the speed of light, which is the fastest speed limit that we have in the universe. And so this is an artist's conception of what a black hole looks like after it formed from a star that was orbiting around another star. So the main object is the black hole, and it was a star that was in orbit around the star to the right, the blue star. It died first, formed a black hole, and now the outer atmosphere of that star is slowly being drawn in. It piles up into that accretion disk, and that gas is slowly spiraling in. And as that spirals in, it heats up, and you can see that it's glowing at millions of degrees. It's glowing red hot on the outside of that disk, and it's glowing white hot on the inside. And it's glowing so hot at the inside that jets of gas are also shooting out up towards the top and down towards the bottom. But all this behavior is happening outside of the event horizon, outside of the black hole proper. So we see black holes not from the black hole itself, but from the gas that's being smashed up and spiraling in and being ejected out of the black hole. And that's the only way that we can see evidence of black holes, or is through these indirect means. The black hole itself, because not even light can escape it after it's entered that imaginary boundary, it remains black, so you can't really see anything. And if you were to fall into a black hole, since the pull of the black hole is strongest, the closer you are, if you were to fall in feet first, what would happen is that your feet would get stretched long before your head gets stretched. And so you get spaghettified, you get turned into a long, thin strand of spaghetti as you get pulled in. So wonderful question. And Asa, are we going to a different school or?
We're gonna head to our chat now. Thank you to Bridges and Garden County Schools for those questions. Those are great. And I just had, I think there was a part of that question about, would it be bright inside a black hole?
Oh, would it be
of the
bright?
light?
Yeah, so towards the center of the black hole where you're falling in, it still might look black or dark, but all around you, you would see light because light is falling into the black hole from elsewhere in the universe. You know, there's light coming, you know, when we're looking out into the nighttime sky or the universe behind me, you're seeing light from stars, from the galaxy, from Mars, from Phobos. And so there's light shining in every single direction. And that light will also continue to shine into the black hole. So you still will see light inside the black hole. But if you look towards the center part of the black hole where you're falling towards, that part will remain black.
All right, very interesting. Very special stuff happens at the center of black holes. So endless intrigue in there. Awesome. So yeah, we've got some questions coming from the chat. And again, to all our friends out there, anytime is a good time to put your questions in the chat room. So please type those out. As soon as something inspires you with a question, just type that in and we'll try our best to answer as many of these questions as we can. But for now, one question that just came up is, where is Halley's Comet?
Where's Halley's Comet? That I don't think I've loaded Halley's Comet into my software. So well, let me see. I stand corrected. We do have a Halley's Comet. So you are all in luck. Let me recenter ourselves so that we're, okay, we don't need the picture of the black hole anymore. But here we can see our solar system. So you can see the orbits of the 4 inner planets and the 4 giant planets. There's also a belt of comets and other icy bodies beyond Neptune. And then there's also the orbit of Halley's Comet. So you can see Halley's Comet has a long elliptical orbit. It's almost like a cigar shape. It's stretched out. And you can see the current position of Halley's Comet down here. So the comet trail or the orbit trails behind it. I don't think we have a model built of Halley's Comet, so we can't fly up close to it. But you can see how different cometary orbits are. So they can have these very stretched out orbits where they can be very far away from the sun for a long time. And then it can take them a really long time to fly back. So what I can do is I can actually fast forward in time. And I just went too fast. So let's see if I can go backwards. There we go. You can see the comet whipping around the sun. And so here we go again. And as it gets close to the sun, you can actually see a tail forming around the comet. And that's because comet tails are due to the gases or the ices in the comet being evaporated away from the heat and light of the sun. And so tails only exist when the comet is closer to the sun, and then they disappear when the comet goes further away. And that's just because when it's further away, there's not as much heating. And so here we can see the comet orbiting. And let's see if we can do one more orbit. So the last time Halley's Comet was in close to the Earth was, I think, around 1987. Can't quite remember the year. So it'll be quite a long time before Halley's Comet reappears again. probably in your lifetime, but we'll have to wait a few more decades. So that's a great question.
Yeah, thank you for that one. And we have another question here. Let's see here. Oh, why does Saturn have rings?
Yeah, that's a great question. Since we didn't actually go to Saturn, we went to Jupiter instead. We didn't get a chance to talk about Saturn and its rings. So here is Saturn. And you can notice there are rings around it that are its most famous feature. But even though the rings look cut off, they're not cut off. It's just the shadow from Saturn being cast on its rings. And so you can see the faint rings in shadow. And then there are the rings that are not in shadow. But you can also see that the rings are transparent. So that tells you that they're not solid objects. It's not a single solid object. And it's not just one ring, but there are many, many rings. And in fact, based on the spacecraft imagery that we sent back, we know that there are hundreds, if not thousands, of individual rings. You can see that as we come up close to it. And I think we can fly up to them so that you can see that the rings are made up of trillions and trillions of bits of ice. So we think the rings are caused by or from a small moon that was orbiting around Saturn. And the moons of the outer giants are often made up of ices because it's a lot colder out here. And you can have ice forming on the moon's surface. And when this moon broke up because it got too close to Saturn, it broke up into trillions and trillions of bits of ice that now stay in orbit around Saturn. And these ice particles can range from microscopic sizes to things that are the sizes of boulders and cars and houses. So they come in quite a range, but for the most part, you can think of them as blocks of ice or ice cubes in orbit around Saturn. So wonderful question.
And then we have another question here about a ring, though it's a very different type of ring than the Saturn ones. And the question is, why can we, and let me make sure I get this right, why can we see the sun but not the ring orbiting around it? And I wonder if maybe they're referring to the corona.
Yeah, they might. There isn't a ring around the sun, but so we can jump to the sun, and what we can do is actually we can fly up close enough to see the solar surface. So the sun is a gigantic ball of gas, and it's about 100 times larger than our planet Earth, and more than 1,000,000 times more massive. So it's an immense, immense, gigantic ball of gas. It's extremely hot in its interior. Nuclear fusion takes place, which allows energy and heat to be generated, and that's what makes life possible. And so the sun, as you can see, looks like another ball. And that's because the sun has lots of gravity that pulls it into a round shape. Now, because the sun is a ball made up of gas, it really doesn't have a solid surface. It looks like there's a surface here, but it turns out what we're seeing is we're seeing the gases to be so dense that it makes it look like a surface, even though it's not a hard surface. Now, you do get a sense that there's also this outer atmosphere to the sun. And so the sun does have an atmosphere that gets thinner and thinner as it goes out. And the sun even has a solar wind. So parts of the atmosphere gets pumped out and it escapes the sun. And it flies, that solar wind, the solar wind particles fly out into the rest of the solar system. And during solar eclipses, you can even see the outer edges of the atmosphere of the sun. It's called, as Asa said, the solar corona. But it doesn't really look so much like a ring as it looks like a big fuzzy kind of donut. It looks sort of wind-shaped. It has kind of angular features. But there are rings that can appear around the sun because we look at the sun, let's say through the Earth's atmosphere. And so on certain cold days, if there are ice crystals in the air, it is possible to see a ring in the air far away from the sun, but that's not really part of the sun. So that's just an optical illusion. So there really isn't a ring around the sun, although there might be things that look like rings around the sun. So really interesting question. A lot to think about because there are a lot of different phenomena that you have to talk about to try and explain an answer to that question.
Very cool. All right, and I think this is a question that has come up multiple times in the chat now, and that is about life on other worlds. So is it out there? Is it possible? What are your thoughts on that?
Well, it definitely is possible. And I'm going to first jump to the Earth because Earth obviously is the one planet and that we know of that has life. It has oceans with lots of water, and we know that water is a necessary ingredient for life. And when we look at the land on the Earth, we can see not just browns of desert, of sand and rock, but we also see the green of vegetation. And that's another sign of life. And if we have specialized instruments that can detect the molecules in the atmosphere, you'll also detect molecules that can be indicative of life. I mean, they're not sure, absolute 100% indicators, but they definitely show that life could be on Earth. And so part of the question is, if we are trying to look at other objects in our solar system, is there life? And people have looked at Mars, for instance, and there doesn't seem to be life on Mars today, or nothing evident. We've sent rovers to the surface of Mars, and I think we even have a picture of what the surface of Mars looks like from one of those rovers. And it's a very harsh landscape. It's a cold desert world. There's no liquid water on the surface. There does appear to be evidence for ice. So the water seems to be locked up in ice. But like I said before, Mars also has evidence that water once flowed on the surface, and it used to be warmer. And we know that on Earth, as soon as it got cool enough for water to exist as a liquid on the surface of the Earth, life formed within tens of millions of years. And so lots of scientists have wondered whether Mars might have formed life early on when it was warmer and wetter, and perhaps there are microbes still hanging on deep underneath the surface. And so that's one of the reasons why NASA is sending a lot of spacecraft, a lot of rovers to explore Mars, and why lots of scientists want to send astronauts there in the future as well. So that's a great question. And then one of the other amazing things is that if we go back to, let's see if I can go back to Uniview, yeah, our planetarium software. We've also discovered more than 5,000 planets around other stars in our galaxy. And so astronomers are intently looking for planets that might be Earth-like or Earth-like enough to harbor life. And we're designing telescopes now that might find evidence of life, just like we can find evidence of life in Earth's atmosphere. So that's a great question and something to keep pondering and thinking about even long after our session today.
And with that, yeah, we'll take that as our last question. Chun, do you have any last comments, words to share with our learners out there?
Yeah, well, hopefully everyone out there got excited and got about what we saw and what you heard about our universe. And if you were so excited to want to learn more, I encourage you to go out and learn more from your teacher, from the school library, from going online and finding resources at NASA and other space news resources to learn more about planets and astronomy and about stars. And there's a lot that you can learn. And like I said, there are plans, or people want to eventually send astronauts to places like Mars in the future. And even though we're planning to send astronauts back to the moon in another few years, the Mars crewed missions won't take place for another decade or two. And so the astronauts today will be too old, they'll be retired. They won't be going to Mars. the astronauts of the future are the ones that are in the classrooms today. So if you are really interested in space, one of the things that you can learn to do in the future is become an astronaut, and perhaps you can become one of those taking their first steps on Mars.
Awesome, inspiring words. So yeah, even if we didn't answer your questions today, please go out there, pursue the answers. It's just a great sign that, there's more curiosity than there is time for us to, to answer all those questions. So thank you to all the classrooms and viewers out there that joined us today. Thank you to Kim and Riley, who are behind the scenes making all of this come together. Thank you, Dr. Kachun, for all your insights and expertise. And with that, thank you all so much. Please join us again next month as we will be looking at super sauropods and fantastic fossils. So whereas today we were very space oriented, next month we'll be much more grounded in the some earthly matters. And yeah, thanks again for joining us. Have a wonderful rest of your day, and we'll see you next time. Bye.
Bye, everyone. Thanks again.